Okay, the lecture today will cover three major parts. The first part will explain what antenna is. The second part will cover a few of the most common antenna that we can see in the military and commercial markets. And the third part will explain terminology in antenna design and antenna area that will mostly help people to understand the line of antenna spec better. So, what is an antenna? Antenna is actually a device that transmits and receives energy from one point to another. How does the antenna do that? It actually transfers current and electromagnetic field upon its surface to a propagating wave. The wave propagates to infinity in the volume that the antenna is located in, and then it meets another antenna that receives this energy, transfer it back to current and electromagnetic field upon its surface, and in this way we actually transferred energy between the transmit point and the receive point. Let's now look on some antennas that we can see in many places. The first antenna that I wish to discuss is the Yagi antenna. The Yagi antenna is an antenna that we mostly used to see on the UHF broadcast of TV. We still see this kind of broadcasting in a few countries, but in many countries we use today cable TV and satellite TV rather than UHF TV. This antenna we still see in UHF communication applications in military applications. The second antenna that I want to discuss is the monopole antenna. The monopole antenna is widely used in commercial markets. If you have Wi-Fi, then you probably have one or more antenna in your modem of this kind. The antenna is omnidirectional. We will discuss this term later. It has a basic capabilities, and it is widely used in the market. The third type of antenna is the fractal antenna. We can see it here. Fractal antenna is a way of reducing the physical size of antennas in order to be able to put them in a limited volume. It is used in surveillance products, and we don't really see it much in the commercial market. The other and very popular antenna is the reflector antenna. The reflector antenna, we can see it mostly in satellite communication and in point-to-point communication. It has usually a narrow beam, and it has very low side lobes and back lobe, and we will discuss all these terms later. The fifth antenna here is a helical antenna. The helical mostly used in order to produce different polarizations than vertical or horizontal. Then we will have to discuss what the polarization is later. This antenna here has a circular polarization, and we will discuss this later. The sixth and last antenna in the slide is the log periodic antenna. The log periodic antenna is a very unique antenna that is a part of a family of antennas that are infinite bandwidth antenna. Theoretically, we can design log periodic antenna from any frequency to any frequency. Practically, it is a little bit difficult, of course, but theoretically, it is possible. Okay, this is another slide that presents different type of antennas. The first one here on the top left of the slide is a miniature ceramic antennas. We mostly see it on small products, which are small relatively to the wavelength in which they are operate, like cellular phones and Wi-Fi cards and modems, cellular modems, etc. These antennas are very small. They has to be located in a very specific place on the PC board that we we implement this antenna on, and they are widely used, but have a lot of substitutions when we want to design miniature antennas. The next antenna is very popular very common in the military market, the dipole antenna. The dipole antenna, sometimes it comes by itself, like here, but in many cases it comes as a part of an antenna array. The big benefit of this antenna is that it has a wide bandwidth, as well as it can carry a lot of power. Mostly this antenna that here in the slide, that if you can look closer, you will see that it is made of pure metal. Pure metal means that we can feed it with a lot of power, and it's really easy to design antennas with which are made from dipoles. The third antenna here is the flat panel antenna. The flat panel antenna is mostly used in the point to multipoint markets, and also used in the repeaters market. It's a very neat and nice antenna, as it has mostly a plastic cover, which we call in the antenna language radome, that makes it beautiful and covering all the metal parts and a PC board that are inside. The fourth antenna here on the left of the middle line is the horn antenna. That is mostly used in the military market applications, and it also used for antenna labs as a calibration antenna. Okay, the fifth antenna here is the flat spiral antenna. The spiral antenna is also a wide bandwidth antenna that is dedicated for producing circular polarization rather than linear polarization. We will discuss these terms later again. The other antenna here on this line on the right side is the conical spiral antenna. Conical spiral, like the log periodic antenna, is an infinite bandwidth antenna. But the conical spiral produces circular polarization, while the log periodic antenna produces a linear polarization. In the seventh antenna here on the bottom left corner, we see a base station antenna which has a wide beam in the azimuth plane and narrow beam in the elevation plane. The wide beam uses, as I said, for base station antennas, and the methodology of this antenna is actually a waveguide that has been slotted. The slots radiates the energy and produces the antenna radiation pattern. The eighth antenna here in the middle of the bottom line is the dielectric resonance antenna. This antenna actually has a resonance frequency which is determined by the structure of the dielectric material that is attached to the probe of the connector that you can see in the slide. This antenna is also a part of the miniature antennas family. It's used mostly in products which are very small compared to the wavelength that they operate in, and also they're used in a product that doesn't have a volume limitation, and we have to hide the antenna, like in military surveillance devices. The last and very popular antenna, which most of you have in your cellular phones in one way or another, is the PIFA antenna. This antenna is actually a metal structure that is folded in a way that it will fit in the limits of the volume that we have. It also can be implemented on very small products comparing to the wavelength, and it is widely used in the market. We can see it everywhere in the commercial market mostly. Now let's start covering some antenna terms, and before we do that, I would like to cover some sizes and markings that are relevant to the antenna to understand antennas. The first one will be the wavelength, which is marked by the Greek letter lambda. We usually use meter units, but we don't necessarily have to do that. But in this lecture, unless otherwise is mentioned, then I will use the unit meters. The other term is the speed of light, which is marked by the letter C. The speed of light will be measured in units meter per second. The third term here is the frequency. The frequency is marked by the letter F. The unit for frequency is hertz, of course. And the connection between those three sizes is that the wavelength equal to the speed of light divided by the frequency. I would suggest here a very convenient shortcut in this formula that will help you guys. If you take the speed of light as 300 and the frequency in gigahertz rather than hertz, then you will receive immediately the wavelength in millimeters. If you want to receive it in centimeters, then you will have to take the speed of light as 30, the frequency in gigahertz, and then you will receive the speed of light, the wavelength in centimeters. The next size here is the antenna aperture size. The antenna aperture size will be used later for some calculation that we will show, and it is also measured in the same length unit, which is here meters. The next term is the gain. The gain is marked by the letter G, capital G. The units for gain, here you have to put your attention, is the dBi. dBi, I will explain later what the I means. The next one is the directivity. The directivity and the gain are connected to each other by the efficiency here. We will show this later. The efficiency units are percents. The temperature, and we will explain how temperature is connected to antennas. The temperature is marked by the capital letter T. It is measured in degrees Kelvin rather than degrees Celsius or Fahrenheit, as will be explained later. Okay, let's now discuss more complex terms in the antenna area. We will start from the plane waves by understanding better what radiation is and how it propagates. Let's assume we have an antenna on this pole that radiates energy to all directions. Then we can imagine a ball that is getting bigger and bigger of the energy that is getting away from this pole in the speed of light. The ball is actually increase its radius, and if we take a slice of it, if we go far enough and we take a small slice of this ball, then it will actually look like a plane rectangle. Then we will look on the surface of the rectangle that we took out of the sphere, and we will see upon it electric and magnetic fields. If we are far enough from an antenna, then the electric and magnetic fields are orthogonal to each other. Meaning, we don't have any other components to other direction, and the propagation is always, as it is described in this slide, away from the antenna. Now the plane wave, which is the slice of the sphere that we observe now, has two characteristics that are interesting. One is that the electric field across the entire area is equal. Any point that we will examine will be the same like the other one, and the magnetic field as well. The other characteristic of a plane wave is that the electric and magnetic fields are orthogonal. This is very important, and the propagation is always away from the antenna. If we draw a line from the antenna to a specific point, then we can know the direction of the propagation of the energy. Now we will start talking about terms that can be found at any antenna specifications that will help understand better antenna specs, what this means, why it is important, etc., etc. The first one is the VSWR. The VSWR is a shortcut for voltage standing wave ratio. It actually represents the following. If I inject an energy to an antenna, let's assume we have an antenna here, then we want to radiate an energy, then we inject power to this antenna. We would have wanted that all the antenna that we have injected to all the energy that we have injected to the antenna will be radiated away. But practically it doesn't happen. Some of the power that we have injected is returned from the antenna, not because we want it to, because this is a physical condition that are derived from the limitation of antenna design, and measuring the ratio between the return wave and the incident wave, the one that is marked here in green color, the ratio between them is represented by the size rho, the Greek letter rho. Another term that is actually the same term that is very common in specs is the return loss. The return loss is actually the same. How much do we loses relatively to the power that we have injected to the antenna. We can see here how the sizes are connected to the size of the term rho. If we take 20 log rho, then we will get the return loss. If we take 1 plus rho, absolute value of rho, divided by 1 minus rho, the absolute, value of rho, then we will get the VSWR. Of course, because they are both related to rho, dependent on rho, then we can have a formula that connected between them too. The return loss, though, is the 20 log VSWR minus 1 divided by VSWR plus 1 as indicated here in this formula. Now we will have to define the shape of the radiation in the entire volume where the antenna is located. If we look at this graph, mostly you will see a graph of this kind, or you will see it in a rectangular graph, but what we see here is actually defines the shape of the radiation pattern of an antenna. Antenna it can be radiated towards all direction, then it will be called omnidirectional. It can radiate only to a specific sector. It can be very narrow, wide. It can be wide in azimuth plane and narrow in elevation plane. It can be whatever we need to add to our application. How do we determine how low these side lobes must be when we design an antenna? In most cases, we have to comply with the specific or specification or standard that we have to meet in all regards to these side lobes, because we don't want to interfere with other stations or other antennas that they receive the same frequency. So these side lobes here has to be set by the standard that we have to be complied with. The back lobe is also set by the standard or spec that we have to comply with. The main beam that I want to say a few more words on can be any shape, almost any shape of a beam that we want to produce. For example, if we have a base station antenna, then we want the main beam to be wide in azimuth plane in order to cover a sector of cellular, in which we have a cellular phones, but it has to be narrow in elevation because we don't need the energy to be spilled to the sky or to the ground that below the pole. In a point-to-point application or in satellite application, this is very important that we don't interfere with the next satellite. The satellites are 2 degrees apart from each other, and I mean the communication satellites, which are fixed in the sky. They are located in the sky in a fixed place, and there are 2 degrees separated between one to another one, and we don't want to interfere with the other satellite. Then we want a pencil beam, pencil-shaped beam. We want it to be narrow and directed only to the satellite that we need it to be directed to. In other cases, like the monopole antenna that we showed before, we would want an omnidirectional antenna. An omnidirectional mean that the main lobe here is spread all around the antenna, all around the 300 degrees that around the antenna. We want equal energy in all directions. Why we want that? Imagine that you have a laptop and you have a Wi-Fi or other modem, a wireless modem in your house. You would probably want to have a connection with the internet anywhere at the house. Then you would want the radiation of the modem to be spread away equally to all parts of your house. In other cases, like in the cellular phones, for instance, we also would like to have an omnidirectional antenna. We would like it to be directed or receive the base station that we are connected to in any position, spatial position that the phone is located. We would like also to receive a signal, a good signal, when we lie down on our couch or we are walking or we are walking around the room. And that's why we would like the energy to be spread away equally. We have arrived to the last slide of this presentation. I hope you enjoyed it. Thank you.